Okay, welcome to Screencast 16. This is the first in a series of 2 screencasts covering condensation polymers. Let's take a quick look at the objectives here. These first 2 objectives are going to be addressed in this screencast. Compare and contrast addition versus condensation polymers, and then describe how they're formed. The second bullet you should actually already know how to do. These last 3 objectives should look pretty familiar because they're identical to objectives that we had in the addition polymer section. Okay, in these 2 screencasts we're going to be going through a number of examples of condensation polymers. You don't need to know them in detail. They are going to be examples that you may see on the IB exam, so you can copy them down if you wish, but it's not necessarily required. You're not going to be asked to reproduce them. I will do my best to highlight when you should be writing things down. Okay, so let's address this first objective first, distinguishing between addition and condensation polymers. How can you tell them apart? Okay, well, let's look at each one in turn. Okay, so here's some sort of key characteristics of addition polymers. They're always going to be made from some kind of unsaturated molecule, so either an alkene, or in some cases we'll talk about alkynes, triple bonded structures. Likewise, they're always made from one monomer. You can just take ethene and polymerize it to make polyethylene. All of the atoms in the monomer end up in the polymer. So in other words, you're not going to form any kind of byproducts like you do for condensation. And then this is a really sort of key one and makes it easy to identify addition polymers. All you see in the backbone is carbon. Okay, so if you see any other elements in the backbone other than carbon, you know that you have a condensation polymer instead of an addition polymer. So like I said, you're going to get atoms other than carbon in the polymer background for condensation polymers. Here's our other key characteristics. Unlike with addition polymers, you need 2 different functional groups to make a condensation polymer. And as a result, you often make what are called copolymers, which means you needed 2 different monomers to come together to make that polymer. Now there are exceptions to this, obviously. If you can put both functional groups in the same monomer, you can just use a single monomer to make that polymer, but more often than not you're using 2 monomers. The other key characteristic of a condensation polymer is the fact that you're eliminating some kind of small molecule as a byproduct. So water is the one that we've been focusing on, but you can get the formation of, say, ammonia or hydrogen cyanide as byproducts as well, depending on what polymer you're looking at. Okay, so those are 2 definite comparisons that you're going to want to write down. You're going to want to know these to be able to reproduce them on an IB exam. Now the other objective that we're addressing in the screencast is to show how condensation polymers are formed. How do you identify what small molecule is being eliminated? I'm going to walk through 3 examples here: PET, Bakelite, and polyurethane. This one we've discussed before as an example of an ester. These other 2 are ones that we haven't talked about before, but they're relevant in our daily lives, and so I think it's important to show them. Okay, so let's talk about PET, which this is used in polyester fabric, plastic bottles, all of those applications. Okay, it is an ester. So, and we've done this before. You're going to have an alcohol coming together. An alcohol coming together with a carboxylic acid, and so the OH from your carboxylic acid functional group and the H from your alcohol are what are eliminated as water. Okay, and then the functional group you end up with is your ester. Now remember, the key of making a polymer is that you need the functional group. You need a dicarboxylic acid reacting with a diol. Okay, so those 2 functional groups need to be at the ends of the molecule so that when you do your first reaction, you can see you have an alcohol at one end, carboxylic acid at the other. Now this is in a position to continue to react and lengthen the chain as shown here. Okay, so once again, here's my carboxylic acid group. The OH from the carboxylic acid and the H from the alcohol are eliminated to form water. Bakelite is another example of a condensation polymer where water is eliminated. Okay. However, in this I do need to show the reaction that's used to make the monomer that goes into making Bakelite. And that's shown in this first step here. Okay. To make the monomer, you react an aldehyde with what's called a phenol. And it's called the phenol, the key features of it, it's an alcohol that is bonded to a benzene ring. When you do this reaction, you end up getting a primary alcohol, CH2OH, substituted onto your benzene ring. And it can be substituted in what's called the second position or the fourth position. And those numbers are related to how sort of far away it is from this alcohol group. Once you form this primary alcohol substituent on the benzene ring, it can then react with the hydrogen that's adjacent to that phenol group on the benzene ring. And so you eliminate water and you end up linking two benzene rings together. The key is the fact that I can get substitution at either the second or the fourth position here. So when the second polymerization occurs, you'll see that you can get linkages in the second or fourth position. And so what you end up with is sort of this open structure that just continues on and on. And so if you look at this structure, what do you think the properties might be? Well, because there are all these benzene rings that are linked together pretty rigidly, you're going to have a nice rigid structure. Okay. And because it's open like this, it's going to be a good thermal insulator. So this is used a lot for, or at least it used to be, for covering electrical wires, electrical boxes, stuff like that, where you need some insulation properties, and you need it to be nice and rigid. So that's Bakelite, and this polymer has been around for a really long time. Okay, the last example I want to talk about is polyurethane, which is, I'm sure you've heard of it before, and so that's why we need to talk about it. It's the stuffing in your couch most likely, but it's used for a ton of different applications. What's interesting about polyurethane is it's difficult to classify as either addition or condensation. And so let's talk about what this polymer looks like. Okay, so it is the reaction of what's called an isocyanate group, which is this guy. And this reacts with an alcohol. And so I'm going to draw it down here so you can see how the bond forms. I'm writing R and R prime just to represent some alkyl groups coming off of the functional group. And when this reacts, the CN bond, double bond breaks to form a single bond instead. And then it reacts with the OH to form this. Okay. And now I can just put the rest of my functional groups on there. The C double bond O still remains and this R prime still remains. Okay, and so this functional group, the NH-C double bond OO, which is shown down here, is called a urethane bond, okay, or a functional group. And so let's talk about how we would classify this polymer. Is it addition or is it condensation? Well, right away you're going to notice that there's no byproduct being formed here. So that really is a characteristic similar to addition. However, many of the other sort of characteristics of this polymer are more like condensation. I needed two different monomers with two different functional groups to form the polymer. In my polymer chain, I have not just carbon, but oxygen and nitrogen, and so that makes it very similar to a condensation polymer. Like I said, you need two different monomers to make it. Okay, so those characteristics are much more like a condensation polymer. Your book calls this an addition reaction, but you will see other textbooks call this a condensation polymer instead. Okay, so hopefully you're able to spot from these reactions which ones are addition versus condensation, with the exception of the sort of unique polyurethane example, and that you can identify the key differences there. In the next screencast, we'll go through some examples of polymer to show the relationship between structure and function. Let's go ahead and stop there. Okay, welcome to our second screencast on condensation polymers. In this screencast, we're going to focus on these third and fourth bullets. Remember, these last three objectives here are really similar to that for addition polymers when we were talking about that topic. We aren't really going to talk about advantages and disadvantages of polymer use because we've already hit that in the addition polymer section. So we're really just going to focus on these. And remember what I said in the last screencast, really I'm just going to go through a number of examples here. These are just examples. Copy them down as you see fit. You're not going to be asked any detailed specifics about these. The primary reason we're going over a lot of these is because we're going to discuss these specific polymers in more detail when we get to later topics. Okay, just to review, when we talked about addition polymers, there's some sort of key structural features that you want to look at in polymers to sort of identify how those will affect your properties. And whether we're talking addition or condensation, these general characteristics still hold true. So chain length is always going to sort of increase your melting point or boiling point of those polymers. The type and orientation of your side groups, so that sort of cis-trans relationship or isotactic versus atactic orientation still applies to condensation polymers. And cross-linking is definitely something that will affect the properties as well, and we kind of talked about that in the last screencast with Bakelite. Hold on, let me get my pen working. So let's see how these properties play out with some condensation polymers of importance. And so the first example we're going to talk about is Kevlar. We're going to talk about Kevlar in a lot more detail when we get to the liquid crystal topic, but we're going to sort of hit this structure-function relationship pretty heavily in talking about this polymer. This was developed in the 60s by DuPont by a scientist there named Stephanie Kwolek. She, I believe, received a Nobel Prize for this work. The key features that Kevlar has is it's really strong but also flexible. And like I said, we're going to talk about its liquid crystal properties later on. So main uses for Kevlar are things like bulletproof vests, but it's used for any application where you need something that's really, really tough to hold up. So sneakers, you name it, Kevlar has been used in it. So the question is, what makes Kevlar so strong? Why is it 5 times as strong as steel in terms of its ability to resist punctures? Well, let's go ahead and talk about that. So here, first of all, let's show how you make it. So we're reacting in amine, and here they're showing this carbonyl chloride compound. Please understand you can also make it from, like if this were an OH group here, a carboxylic acid. So we're forming this amide group here. That's the functional group that's present in Kevlar. The key features that give Kevlar its strength is the fact that we have these benzene rings and we have them in this sort of 1,4 orientation. So the functional groups are right across from each other, across from the benzene ring. And so what does that do for us in terms of the strength of Kevlar? Well, the key is, if you look at the orientation of the amide group, the amine, or the hydrogen on my nitrogen, and the oxygen on the C double bond O are opposite of one another in the chain. Okay, so NH and CO on opposite sides of chain. Okay, and so this is important because what that does is allows for some really significant hydrogen bonding between adjacent chains. Okay, and so that's shown in this picture here. you can see that the hydrogen, this orientation shows that they're on opposite sides of the chain. The hydrogen from this NH is hydrogen bonding with the oxygen on the C double bond O on an adjacent chain. And because that happens on a very regular basis, you get very regular hydrogen bonding. And so you can almost think of it as Velcro. These things are really stuck together in there. And that is what gives Kevlar its strength, the fact that this thing is held together with this extensive hydrogen bonding network. Okay, another pretty cool feature that you can, or a property that you can give to polymers is you can make them conductive. Okay, and so the sort of traditional example of a conductive polymer is polyethylene. Okay, and so remember this is an alkyne group, not one that we've talked about much, but it's a triple bond carbon-carbon. Okay, and just like with alkenes, you can do an addition polymerization to make polyethylene, which has this double bond in the structure. Okay, now you know that double bonds restrict rotation. Okay, and so we can end up with cis and trans orientations of this double bond. And so if you can isolate either the cis or the trans of polyethylene, they actually end up being different colors. One is red and one is blue. And the trans orientation is a semiconductor, okay? And that's due to what's called conjugation. Every conjugation is alternating single and double bonds. Okay. You see this in benzene as well. Okay. And what that allows us to do, and certainly for benzene, you'll obviously, or you've seen it drawn this way before, that's to represent significant delocalization of those pi electrons along this bond. Okay, so the pi electrons, that second bond in the double bond, can essentially move all up and down this chain because of the conjugation of those bonds. Now, so that's what makes it a semiconductor. Now, we want it to be a conductor. And so the way you do that is by removing just one electron from the system. And the way you can do that is using a process called doping. And what you can do, the doping agent that you can use here is iodine. And so this splits into iodine radicals, which can then react with the double bond in one double bond in your structure and make I- and C+. Okay, so you can see this double bond is missing, and you end up with a carbon radical here. That single electron can now start to move down the chain, and so that's what this picture is showing. That sort of unpaired electron is what allows this polymer to conduct. Okay, now you think, oh great, plastic wires, this is awesome. These are quite complex to make. For this particular polymer, there's a lot of negatives to it. It's not very stable. There's issues, and so there's a lot of research going into making conductive polymers. We're going to come back to this topic and these particular examples when we get to the silicon and photovoltaic cell topic. Okay, I do want to hit just a couple other examples of modifications. So in the previous examples, our Kevlar example is really just all about structure-function relationships. This is also conducting polymers, is also discussion of the relationship between structure and function, but also there is some modification going on here. We're adding iodine to increase conductivity of these polymers. Here's some other modifications you can make with polyester, okay? And so one application for polyester is in fabrics, and so I don't know, you guys are too young, but to remember those sort of 70s polyester suits, they're really disgusting, feel awful, and have a lot of issues in terms of using it as fabric. They're very hydrophobic, so they don't really pick up dyes very well. So it's hard to dye 100% polyester. In addition, there's significant static buildup in these addition polymers, especially when they're used as fabrics. And so the solutions to these problems are simply blending. Okay, if you blend other fibers, other polymers in with polyester, you'll be able to more easily dye it and reduce the static buildup issues with those polymers, so they lay nicer on your skin. And then here's some other options that you could do is simply modify the polymer chain. So we can do some structural changes, or we can do some sort of post-structure modifications of that polymer. Okay. All right, last example. I did want to come back to visit polyurethane to show, because this is a common use of polyurethane, is in insulation applications as well as in, like the foam that fills your couch. So how do we make polyurethane foam? All you do is you can add just a tad of water. Add a little bit of water to the monomers before you mix them. And what happens is water reacts with isocyanate and it produces carbon dioxide. Okay, and so this drawing, although it's not very good, it's just supposed to say HOH down here. Okay, so just like when you're reacting an alcohol with an isocyanate, I can also react water with an isocyanate. Okay, and so you end up getting this intermediate structure, which then decomposes to form an amine and CO2. Okay, it's the CO2 now that can act essentially as an in situ blowing agent. Okay, so this polymer gets made, carbon dioxide is being formed, and it just causes that polymer to completely expand. And so you end up with a flexible foam. So this is used in like spray insulation in houses. It's usually made on site and formed to the form that you need in terms of that stuff. Okay, so that is our discussion of examples and modifications. Like I said before, you don't necessarily need to know these in detail, but we're going to come back to a lot of these polymers later in this unit. So now you're ready to go and do the organic mechanism and condensation polymer questions in the worksheet packet. Let's go ahead and stop there.